Bom dia, senhoras e senhores. Iniciando as atividades desta manhã, no segundo e último dia do Fórum Sustentabilidade Hídrica, Perguntas, Desafios e Governanças. Teremos a palestra Micromesh Microorganisms para coleta de água e tratamento de esgoto, com o palestrante Daniel Lipschits. Ele é diretor da Fundação Biosfera, com plataforma internacional na sustentabilidade econômica, tecnológica e social.
Bom dia. Infelizmente, meu português não é bastante bom para fazer uma palestra assim em português, so I will switch to English. In this presentation, we will take a look at two technologies, and I think it's interesting to have also sort of a better look into the technological aspects that may relate and be relevant to the debate on the crisis that was yesterday and will continue today. I will do like a little background, a little backtrack, and then get into the technologies because we only have half an hour for this. Basically, water, the metabolic challenge. Let's, without further ado, have a look at what is a metabolic challenge. In Europe, we talk about a circular economy. And a circular economy looks at what's called the urban metabolism. Now, urban metabolism, it's nothing complex. Just as we have metabolism in our bodies, so does a city or have a metabolism. Also, industrial productive change have metabolisms. What does that mean? Basically, into the city, we have flows of energy, food, water, and goods. And the output of that, for instance, energy in emissions, food in organic waste, water in wastewater, and goods in inorganic waste. Now, looking at the footprint of a city, we see that the more the loops, the cycles of these flows, these metabolic flows, are not closed, the larger the environmental footprint of the city. In other words, the environmental footprint of the city exceeds the geographical footprint. So in a circular economy template, we look at how the loops for water, energy, waste, and food can be closed. And in the different studies, in the different technological developments in this sector, water is key. So basically, a bit about the background. We developed a system called Cidade Circular, which specifically looks at the decentralized possibilities to deal with these metabolic flows in the Palestra urban environment. And we introduced this subject exactly a year ago at FIESP. And already then we were talking about the arguments for decentralization, specifically in the water sector. And we put forth some data that we had studied. For instance, that in the urban periphery of the Sao Paulo municipal area, between 40 to 60% of the households are not connected even to the most basic sanitation infra. But that at the same time, 25% of all collected sewage is lost, 25.7% of all treated water is contaminated the moment it hits the supply chain, and then within that supply chain, about 30% is lost through leakage. Now, these are numbers that everybody is talking about, but last year we didn't get the feeling that in that forum at FIESP there was much of a crisis atmosphere. We also looked at some other data, for instance, the distribution of green area per capita, and correlations like the mortality rate in the periphery, which is associated with the lack of basic sanitation, is of course much higher than in downtown Sao Paulo. But then when you look at the mortality rate as a result of acquired diseases that are associated with contamination, specifically soil and water contamination, the rates are much higher there. So in other words, the argumentation for decentralizing the water infrastructure is that you already have an overburdened system, and if you would want to make connections for those households that are not connected yet, you're going to even overburden it much more. Again, I said, from where I come from, which is Holland, if we would have this kind of percentages, there would be a crisis, like governments would fall, utility companies would go bankrupt, people would go to the street. But we found already last year that this is sort of business as usual. So what is this crisis? Is it really a crisis of drought? I will not go too much into this slide, but basically from the point of view of circular economy, of the urban metabolism, the higher there's an overlap between natural ecology and monetary economy, the higher the extent of sustainability. Because in the natural environment, the function of symbiosis takes care that all metabolic loops are closed and they are multidirectional. Whereas in our built environment, which is linear, the loops are sort of dots connecting the line and the flows are in one way. So we look at systems, technologies, methodologies, approaches that can close these loops and go to more circular systems, which by nature are more sustainable. Then let's take stock. In a very straightforward way, I will run the risk that all this may be very simplistic, but I have the urge sort of to take stock after the debate yesterday, because we talk about this crisis and the focus has been very much on the dwindling levels in the reservoirs. But what really is this crisis? Let's say there's a scenario in which the hydrological system, the rivers, the headwaters, from upstream to downstream in Sao Paulo state and specifically in the urban areas would not be contaminated. The question is, would there be still a drought crisis? If we could use the rivers for water collection, then would there really be a problem? In other words, the water security in the current water infrastructure is pretty linear, or in other words, monofunctional as it's called, meaning that we have a hydrological system with headwaters, with rivers, with tributaries, with a high degree of degradation of the riparian ecosystems and ecosystems in general, and a lot of loss of bioretention. Then we are dependent for our water supply system on the reservoirs, and by now levels are dwindling. Now whether this is due to climate trends, meteorological trends, man-made or not, in reality, of course, it's very important to understand about that, but on the ground, we can do many things to increase this water security. For instance, the loss of precipitation due to deforestation as a result of the lack of biotic pumps, which is a fancy word for trees, creates an atmospheric block in which we don't have enough levels of precipitation to replenish the reservoirs. But again, basically, the crisis may be one also of management and government, which was already established yesterday. A crisis of a derelict linear infrastructure which can not anymore interact and meet the requirements of the growing urban population, which is also more diversified. Maybe it's a result of trying to tame the hydrological system through the system of reservoirs. And maybe it's also a function of the dependency on those reservoirs for our water supply. And then for sure, using them as open sewers makes the rivers a problem rather than a solution. So in the same very straightforward and simplistic manner, what would we need? What could we do? And what could we do now in order to avoid this massive problem of overhauling large infrastructure connected to the water supply and wastewater treatment? So we can look at water reuse, which will reduce the supplied water out of the reservoirs. For sure, we should look into creating gradual steps in reducing the load of sewage directly into the rivers. In other words, using rivers as open sewers. And then the water crisis is real. There are people really suffering, really being hit by this, scrambling for potable water on a daily basis. So there needs to be done something now to alleviate the situation of these people. And I think most importantly is to showcase systems, to implement pilots so that we can show that this is possible in Brazil, in Sao Paulo, and we don't have to wait for a long-term, multi-year planning stage that is implemented gradually to remediate the current crisis. So, in all the lectures until now, we saw pictures of the current water drought are featuring pictures like this, but what I didn't see is a picture like this. Maybe we don't really realize what it means if, on a daily basis, for a prolonged period of time, a young boy has to go out trying to scramble for water. It's a serious problem. It's really something that uproots, let's say, the daily routine in life. And the first technology I want to show, something that is very simple, that is community-based, it can be implemented with a community, by a community, doesn't require a top-down structure, and actually it's pretty efficient. So, without further ado, it's a project that we're developing together with a colleague of mine called Arturo Vittori, an Italian designer and architect. It's called Warca Water. And Warca Water is a very simple structure. It's a structure called a grid shell, which is self-supporting. It's made by a design method called parametric design, which I will not talk about. And basically you have an outer self-supporting structure, in this case made out of bamboo, which is another story which I also want to talk about. And within that structure, a micromesh is suspended. And basically this project was developed for remote communities in Ethiopia that have problem with their water provision. And the micromesh harvests atmospheric water, so dew water, water that is basically in the atmosphere, condensates on the filaments of the micromesh. And with the first pilot in Ethiopia, we were surprised to see, even without further developing the micromesh, looking into optimizing the system, already between 12 to 20 liters of potable water are collected this way, which is good in that context for 3 to 4 households in terms of providing them with potable water. We don't see a reason why a project like this could not be implemented within urban communities in Sao Paulo. Actually, this was also presented last year at Mackenzie. We're talking with Braskem to do the R&D on developing a bioplastic micromesh. And this year, July, we are organizing a workshop. So here you can see the evolution of this technology. So in 2012, there was the first little prototype in Ethiopia that produced the... I'm sorry. There seems to be a technical problem. So that was a little technical intermezzo. It's a lecture about technology, so I guess that's proper. So we are organizing this workshop in July within the CAD Futures. CAD Futures is an annual conference about computer-aided design. This year it's actually organized by Unicamp together with USP and Mackenzie, and the subject is the next city. So here we can see the evolution of the Warca Water bamboo tower. In 2012 we had the prototype for Ethiopia. In 2013 it was an upscaled version of that for Italy. Then last year in 2014 yet an upscaled version for a project in Lebanon. And then this year, as we speak, Arturo is now in Ethiopia doing even a further upscaled version, which will actually be able to service potable water for small towns, small communities, and also Project Shadow. And the workshop will be about if the further evolution of this technology will happen in Sao Paulo, what would it look like? So we will have 2 days with designers, architects, artists, engineers, software developers, to produce a line of Warca Water towers for Sao Paulo. And then afterwards we will implement that as community projects in the Sao Paulo urban regions. Then there's another technology. This is in cooperation with Geotectura, which is an architecture firm that is licensed to the Haifa Technical University, which is called WADAIR. And other than the Warka water tower, this is really a product that could be developed, but could be, for instance, developed by the people that are involved in the communities and are familiar with this technology to sell, let's say, to more high-end markets. It's the same principle, only here we use a more engineered micromesh, that the yield of the micromesh is about 1 liter per 5 square meters. And of course, there are many factors that influence the efficiency of the micromesh. And basically, those are parameters like the angle, the color, the wind speed, and of course, the humidity level of the atmosphere itself. And also here, we've used a bamboo frame. Water is collected into a bag that can then be placed in a device for potable water. The reason why I said that this is more high-end, because this micromesh actually allows for the inclusion of a PV thin film, and also electricity is generated. For instance, enough electricity to power up your electrical devices like computers, mobiles, and you name it. So basically, the costs of a Warka water tower, the bamboo Warka water tower in a mid-size version is about $200, and that's the cost price of a pilot. So if you would create more, we probably can bring this down to $100 per pilot. So if this is shared or donated to a community, this is really a technology that even financially or budget-wise could be implemented now. A unit of water air in cost price as a prototype is about $150. But then, of course, the yield is much less because they're smaller units. So this is one example of how maybe a simple technology and something that looks like a gadget actually really can provide potable water in quite good amounts to communities that need it. The second technology is a technology by a partner of Fundação Biosfera, Biopolis, and that more looks into the realm of decentralized wastewater treatment technology and water reuse, which is important because if we can implement wastewater treatment decentralized, it's possible to catch the sewage, the contaminants and the pollutants before it actually reaches the rivers. Now, Biopolis is a spin-off company from Organica Water and Organica Technologies that under the supervision of Istvan Kenyeres, the founder, has done 200 similar type projects throughout 3 continents using this unique technology, and all within the context of urban integration and decentralized wastewater treatment and water reuse. It's important maybe to understand that in our perception, the highest tech, because we always talk about low-tech, high-tech, breakthrough technology, next-generation technology, but the highest tech, from our perspective again, in terms of wastewater treatment, is the rhizosphere microorganism symbiosis. Now, yesterday there were some examples for wetlands and the use of ecosystems and the restoration of ecosystem services as a function to treat water. However, the technology that we talk about is not really comparable because wetlands typically work with the secondary plant metabolism, which is the contaminant and pollutant uptake into the plant itself through the roots. And then pollutants and contaminants are encapsulated either on a cellular level or on the level of the tissue of the plant. But what we talk about is the rhizosphere, that is a habitat for many endemic species of microorganisms which differ per plant species. And these microorganisms, of course we know this from active sludge technology, which actually this year exactly is 100-year-old. These microorganisms, bacteria, germs, actually are great agents in treating water. So Biopolis has established a pilot plant in Budapest, and a pilot plant like that is simply above ground, a botanical garden. Below ground there are a number of installations for tree treatment, but basically we talk about a garden with many different bioreactors, and the bioreactors of course are the plants. Now, the reason why it's in a greenhouse is because in Budapest, because of climatological reasons, it's not possible there to do it without a greenhouse. But here in Brazil, it actually could be a garden, it could be a park, and would be perfect to integrate inside urban landscaping, public green. Maybe we should let Istvan take us a little bit through the pilot plant. Before that, I must say that at the moment, Biopolis is creating an order portfolio for larger installations in Singapore, Malaysia, Japan, China, and also Germany and the Netherlands. Next week, there are some negotiations in the United States, and we really would like to implement a pilot plant. Why not actually in the university campus here of Unicamp, and bring this technology to Brazil. So Istvan will talk, I will translate because he speaks Hungarian, it's subtitled in Dutch, I will translate in English, and then she will translate it into Portuguese. So here below the raw sewage arrives. First there is a phase of primary filtering, taking out the larger parts out of the sewage, like food rest, plastics, condoms, big things. Then it goes, that goes into the incinerator to generate electricity. Then this filtered water goes to the next phase, in which even smaller particles are filtered out. After that, the water is going into the bioreactors, the biological phases. So here you see, it's a greenhouse. This is where the biological treatment is taking place with different bioreactors. Here, all the organic pollutants are being taken and processed out of the water, out of the sewage. And of course, we call them contaminants and pollutants, but for the microorganisms, it simply is food. The traditional active sludge process was invented in 1912. And it used only about 100 different species of microorganisms. We, in the meantime, are using many thousands different species of microorganisms to perform the water treatment. And also, we started to work with plants. Not because plants are such great contaminant uptake agents, but because of the root system, which has a unique surface that creates a perfect habitat for microorganisms. So the only pollutants that remain are hormones and pharmaceutical spores, but we also identified the bacteria that can even filter this out of the water. If you can create a habitat in which organisms and other natural microorganisms and other natural organisms can thrive, then you create a very efficient ecosystem. An installation like this with a botanical garden of around 400 square meters can service 10,000 users. And it's only 1/5 of a traditional wastewater treatment plant. But the biggest change is the psychological and cultural effect of such an installation. Would you like to live across a wastewater treatment plant? I don't think so. But what if you live next or in a botanical garden that, by the way, also treats your wastewater? That's a completely different experience. I think people should start to think differently, especially people that live in the cities and that aspire to live in and around green areas, especially if it treats their wastewater and produces clean water that can be used for many different purposes. So that was a little introduction by Istvan by proxy. Then basically, we call them productive green areas, which again are fully fledged distributive wastewater treatment plants for water reuse. And again, just in this diagram to explain better how it works is we have above ground the plants, then the rhizosphere is suspended in the water. Now typically the rhizosphere, the surface of the root system, is not sufficient to create a wastewater treatment system that is both technically and economically viable. So there needed to be a means of increasing the root surface artificially. Then more in detail, there are the specially selected planted ecosystems, which is a fancy word for different plants. There's a catalog of about 1,200 different plants that all of them have different endemic microbial species for different functions in dealing with different contaminants and pollutants in wastewater. And about a third of this plant species actually are native species in Brazil. Now, in order to increase the surface area of the roots, there is a special artificial media developed which allows for the microbial colonies, if you will, to create a biofilm on roots. And this is important because in traditional biological reactors, and for instance also in the activated sludge, the microorganisms actually are suspended in the water. They're like in a soup. And it's basically like us. If we are in the water, yeah, we enjoy. But all our actions are a function of not drowning. So the same for microorganisms. One of the reasons wastewater treatment plants need to be oxygenized. But when the microorganisms attach themselves to a surface and create habitats as a biofilm, then the activity of the microorganisms is much more efficient, and they are possible to deal with a much wider range of metabolic functions, another word for breaking down different contaminants and pollutants. So just having a bit closer look at that, a section of a natural root and the biofilm it will allow to form on the surface never exceeds 1/10 of a millimeter. But in the artificial root, this artificial media, the biofilm can range from 1 millimeter all the way up to 1 centimeter. And then, of course, in terms of the spatial insertion of the artificial surface where microorganisms can create habitats, there's a ratio, always 1 to 100, can range up to 1 to 10,000. Also, the artificial root has a much higher biodiversity than the natural root. It allows up to 2,000 to 3,000 species per bioreactor. Then in terms of the sequencing of this installation, so just to recap, there's the pre-treatment, taking out the larger part of the sewage water. Then there are specialized microbial communities, different types of plants with different types of endemic microorganisms that can treat different types of wastewater. Based on whatever context. You can think, for instance, that these type of decentralized wastewater plants are very good for hospitals, for shopping malls, university campuses. They can be implemented in clustered households like condominiums, but also favelas. They always will look at what are the local requirements of the user, and then the ecosystems, that is the variety of plant species, will be made accordingly into this reactors. Then the output through a phase separation, there are the created water products and the biological products. So the water products, just as an example, for instance, is domestic non-potable for flushing toilets, showering, doing dishes. There's no reason why the water with this type of bioreactors cannot be upgraded to potable water, but many times legislation doesn't allow wastewater to become potable water, even though with this system we already created water of a better quality than mineral water from a spring. Then irrigation water can be created. For instance, the microbes can be controlled in such a way that they will leave certain nutrients in the wastewater. So it makes much more sense to irrigate land where the nutrients are already in the water, which is wastewater, rather than using upgraded utility water and then add the nutrients in terms of synthetic or whatever types of fertilizer. Then there's a whole range of processed water for different industrial uses. And for instance, demineralized water. Demineralized water is a very good agent for heating and cooling. And just for your information, for instance, in the US, 95% of the water used in air conditioning is potable water. And in some cities, that constitutes 50% of all potable water use. So replacing this with reused water out of wastewater makes a big difference. Then in terms of the biological products, Basically, you have a lot of organic waste from the wastewater itself, even though much less than in conventional systems, because these microbes, other than eating the pollutants, they also eat each other. So typically you're left with much less sludge. And other organic waste, for instance, if you're in a hospital context or a shopping mall context, there are enormous streams of wasted food on each day. And this can be processed in a biorefinery and transformed into valuable products like carbohydrates, proteins, fats, lipids, or for instance, into energy or biomaterials. I will not go into this because I think I will run out of time, but basically the way that the microbes are controlled, manipulated if you will, is through a process of quorum sensing. Quorum sensing is the coordinating of the microbial species through gene expression. They use pheromones, just like plants, just like we use pheromones to, for instance, attract each other. And through the understanding of the process of the production of the pheromones for which function, we can start to communicate with the microbes. And we can, for instance, influence the biofilm formation on the habitat, either of the root system or the artificial root system. Or we can start to control metabolic functions, switch them on and off, make them select certain contaminants, make them process certain contaminants in certain ways, make them resistant or non-resistant to certain contaminants, etc. This I will not talk about at all. But then let's look at a project in development. Let's look at the project in Budapest. That's also where this technology was first developed. So this is the central green zone of the city of Budapest, where there is a large zoo. There's the museum district. There's a residential and commercial. I'm having this problem again. I'm sorry. I'm sorry, people. And this area is about 1/3 of the size of Central Park, and it serves about a quarter of a million people. And the reason why the productive green area is projected at the zoo is because the zoo is being renovated. It's like a very large project. Basically, this is what it looks like in terms of the architectural projection. So here we have the water recycling finding place, and the plants you see here, they are the actual bioreactors. This is the wastewater treatment. So they are plants inside the structure. And then also here you have the biological production, which I just spoke about. There is out of the biomass that remains of the phase separation, animal feed production, which is very handy in the context of a zoo, and the energy production for all of the zoo, as well as organic waste processing. And it's all integrated into the visitor center of the Budapest Zoo itself. So just if we look at this area, it's being encapsulated into an architectural project. Whether you like it or not, it's the utility infrastructure actually becomes a public space. So if we go inside, this is an artist impression. So here we have our wastewater treatment plant, which are just sitting bioreactors, providing a nice environment in this zoo. Then also we are developing a microscopic zoo. So this is the part of the zoo that will show the life and anything that's interesting about microbial species. And then we have a Palace of Water Miracles, where we show what microbial species can do with water. And actually, we show also how this process works. So it's all open to the public. Then, if we look at it, so what can you gain with this? Well, you can gain 65% reduction in primary energy uses. You can reduce 95% of the freshwater requirement, and this is what we talk about these days. How can we reduce the water requirement? Here you go, 95%. So only 5% of the water requirement of a very large area remains. 95% is reduced, and 90% reduction in waste generation. So how does that then translate into numbers? For instance, out of this specific project, which again, it's a visitor center of the zoo integrated with its utility infrastructure. So we generate renewable energy worth of 9 megawatt, which is all the electricity requirement of the zoo. Recycled water is 10,000 cubic meter per day. The organic waste processing is 5 tons per year. And the investment costs is, including the architectural project, 10 million euros, which the return on investment is 6 years because you're generating your energy with a surplus. You create your own animal food, and you have a whole range of biomaterials, raw materials that can be sold out. So what in the past would be actually a cost of the utility company, now it's a gain. Then here are some other projects that are being developed now. This is the wastewater treatment and energy provision for the Astana World Expo in Kazakhstan in 2017. There is in the same country and also in Singapore, the so-called bio-industrial park, which looks exactly at the same technology, but then upscaled to deal with all the flows of an industrial condominium. In this case, for instance, a bioethanol plant, biopolymer factory, biopharma plant, and a fertilizer plant in the biochemical cluster. And in the agri-food cluster, we have a meat factory, a compost factory, a greenhouse, and a biofood factory. So wrapping up, this technology can also be introduced as a so-called disruptive technology. We call them the water moles or the water hubs for development areas, such as favelas, which are modular, scalable. They can be customized to meet any requirements. They can be standardized, so they can be mass-produced, lowering the price per unit. So the question really remains, where do we want to go? We want to remain in this sort of alien landscape of traditional wastewater plants, or do we want to go to these productive green areas, integrating and decentralizing our utility infrastructure into productive green areas in the urban environment? So just a thought that I was having yesterday during the lectures when there was a talk about the requirement for cultural change. And I think really if we talk about a crisis with regard to the utility infrastructure, not just water, also energy, the extraction of resources out of the natural environment. Here in Brazil, there may be some kind of cultural crisis where a tipping point is reached. Technologies, methodologies, approaches need to be diversified, need to be decentralized. The top-down model, the vertical line has to become horizontal. So, of course, debate and study is adamant, and the university as sort of a switchboard between the public sector and private sector really has a function. But then let's not forget that study and debate can and many times precedes cultural change, but real cultural change is brought about by first-hand experience, by, if you will, an experiential context. And this is the reason why I think it's important to implement pilots and showcases. And we work with a very large portfolio of technologies, some with a high technology readiness level, some already implementable, some just ideas of PhD students that still need a proof of concept. But let's try and see how together we can implement the showcases so we have a point where we can point our finger to and say, look, this is possible in Brazil, and this will eventually help us to deal with the current crisis and possible crises ahead. So, thank you very much for your attention.